Hello everyone and welcome to the second part of our lecture. In the previous part, we have talked about heat engines, heat pumps, and refrigerators and how do we characterize their performance or their efficiency. In this lesson, we will be particularly discussing the Rankine cycle. The Rankine cycle is one of the many thermodynamic cycles that involves the generation of power from heat. Let's begin. The Rankine cycle is part of a family of cycles called power cycles. Power cycles are four-step thermodynamic cycles that describe the generation of work from heat energy. These power cycles follow the template four-step process that is compression, heat addition, expansion, and heat rejection, just as what we have discussed for heat engines. However, power cycles can have different conditions for the four-step processes compared to that of a simple heat engine. We can classify power cycles based on the nature of the working fluid. We have two types. That is, if the working fluid is recycled in a closed loop, an example of that is the Rankine cycle, which we will discuss in detail later. And another class of power cycles involve a working fluid that is continuously replaced. Common examples of this are internal combustion engines such as Otto cycle and diesel cycle. And another example is an external combustion mechanism. An example of that is the Brighton cycle. For this lesson, we will focus on the Rankine cycle. So what is the Rankine cycle? This is the basis of modern electricity generation from heat. Usually, we can see the Rankine cycle in our power plants. The source of heat could either be from combustion or other sources such as geothermal and solar heating. These are the four basic processes that correspond to the four steps in the Rankine cycle. The first is fluid expansion in the turbine. Second, heat rejection in the condenser, wherein the cooling water recirculated here absorbs some of the heat energy of the output of the turbine. Next, we have fluid compression in the pump. This is necessary to add pressure to the fluid in order for it to flow into the boiler. And the final step is heat absorption in the boiler. It is in the boiler wherein our heat input coming from either combustion or other sources gets transferred into our working fluid, enabling it to be evaporated. You can think of the Rankine cycle simply as a series of the changes made into the working fluid. The most common working fluid in the Rankine cycle is water because water can be easily evaporated and condensed, and we have vast sources of water, so it's very common and it is non-toxic. The water undergoes four distinct steps in the Rankine cycle. Water vapor is expanded in the turbine. Water vapor is condensed into liquid in our condenser. The liquid water is pumped to increase its energy, and then finally in the boiler, the liquid water is evaporated to become vapor, which then enters the turbine. Let us consider each of the processes in the Rankine cycle. Let's start with the turbine. The turbine is where the useful shaft work is generated. It is connected to a generator to convert the mechanical energy to electrical energy. In reality, the output of the turbine is shaft work. That shaft work is translated to an electrical generator that generates the electrical energy. The input to the turbine can either be saturated or superheated vapor, and the outlet is a saturated mixture. Commonly, the input to the turbine is a superheated vapor, and that serves to increase the amount of shaft work that is being extracted from the turbine. If we consider the turbine as our system with stream 1 entering and stream 2 exiting, we have here the simplified energy equation of the shaft work generated by the turbine is equal to the mass flow rate of the steam or the working fluid multiplied by the change in enthalpy. This change in enthalpy is simply H2 minus H1, or the specific enthalpy in stream 2 minus the specific enthalpy in stream 1. This is just a review of our previous lessons. Next, we have the condenser. The condenser is a heat exchanger that removes heat from the process fluid by using a cooling fluid, usually water. This is a closed-type heat exchanger wherein the cooling water does not mix with the vapor coming from the exit of the turbine. The input to the condenser is usually a saturated mixture, and its output can be a saturated liquid or a subcooled fluid. If we perform our energy balance in our condenser, we will arrive with this equation wherein the heat removed in the condenser is equal to the mass flow rate of the working fluid times the change in enthalpy of the working fluid, that is H3 minus H2. Remember that stream H3 is the output of the condenser, stream H2 is the output of the turbine. Next, let's have the pump. The purpose of the pump is to increase the pressure of the working fluid to make it flow into the boiler. So we are specifically saying that this is a pump because this services a liquid. Remember that the output of the condenser is either saturated liquid or subcooled liquid. The output of the condenser, that is stream 3, is the input of the pump. Considering the pump as our system, this is our simplified energy equation. the shaft work used by the pump is equal to the mass flow rate multiplied by delta H. Delta H in this case is H4 minus H3. H4 minus H3. H4 is the outlet of the pump and the inlet to the boiler. Stream 3 is the outlet of the condenser and the inlets of the pump. And finally, we have the boiler. The boiler is also a heat exchanger that adds heat to the working fluid. And the heat that is being added to our working fluid comes from combustion, such as for coal and diesel power plants and other sources of heat. The input is usually a saturated liquid. This is what comes out of the pump, and its output can either be saturated or superheated vapor. If we perform an energy balance in the boiler, we will have the heat added to the boiler is equal to mass flow rate times delta H. Delta H is equal to H1 minus H4. H1 is the output of the boiler and the input of the turbine. If we consider the entire Rankine cycle as one big system, we can characterize its thermal efficiency. Just as what we have discussed from heat engines and heat pumps, we can determine the value of the thermal efficiency with the ratio of what you get over what you paid for. The purpose of the Rankine cycle is to generate shaft work, so therefore what we get is the net power output of the system. The net power output is simply the absolute value of the power generated by the turbine minus the power consumed by the pump. The power generated by the turbine is in absolute value because this has a negative sign based on our sign convention. Remember that work being done by the system has a negative sign. So in this equation, we don't want the negative sign because that would alter our efficiency. And in the denominator, we have what you paid for. We are paying for the heat that is being added into the boiler to vaporize our water. Therefore, the thermal efficiency of the Rankine cycle is the net work generated divided by the heat added to the boiler. If we go back to our derivations, we can substitute the delta H values for the turbine, pump, and boiler as H2 minus H1, H4 minus H3, and H1 minus H4 for the boiler. You would also notice that we have dropped the mass flow rate because the Rankine cycle uses a working fluid in a closed cycle. Therefore, if everything is in steady state, the mass flow rate of the working fluid going through the individual parts is constant. So that would just cancel out. We now have our final equation for the thermal efficiency of the Rankine cycle. That is 1 minus H2 minus H3 over H1 minus H4. You don't need to memorize this equation because this is just derived from our definition of the thermal efficiency. So in case that you forgot this equation, you simply take a look at your diagram for the Rankine cycle and then characterize what you get over what you paid for. That is the thermal efficiency of the cycle. Now, let us talk about the different iterations or the different types of the Rankine cycle. Let us start with the base case and the simplest scenario. This is the ideal Rankine cycle. The ideal Rankine cycle is considered as the base case scenario for determining the efficiency of a power plant, and all of the steps are considered reversible. If you take a look at our temperature entropy diagram here, the conditions of each of the streams can be identified. For example, stream 1 is the input to the turbine. And based on this TS diagram, stream 1 is a saturated vapor because it is on this line here. From stream 1 to stream 2, our step is fluid expansion in an isentropic turbine, meaning that the entropy is constant. So from stream 1 to stream 2, we have a vertical line. That means that it is constant entropy. Stream 2 is a saturated mixture of vapor and liquid because it is inside the curve here. If we have access to the actual temperature entropy diagram of the working fluid, you can determine the values of the properties at stream 2 by using the lever rule by determining the quality of your stream. From step 2 to step 3, we have isobaric compression, which is our condensation step. Our condensation step also proceeds isothermally because we are just changing the phase of our working fluid from a vapor to a liquid. So that is constant temperature. Stream 3, as you can see in this curve, is now a saturated liquid. From stream 3 to stream 4, we have fluid compression in an isentropic pump. Isentropic, therefore from step 3 to step 4, that is also a straight line. For stream 4, we have a subcooled fluid. And then finally, for the last step, we have stream 4 to stream 1. Notice that it is not accomplished in a single step. We have from 4 to A and from A to 1. Step 4 to A represents the heating of your subcooled fluid up to its saturated liquid conditions. And then from step A to 1, this represents the actual evaporation. It goes from a saturated liquid to a saturated vapor, and the cycle begins again. Okay? This is the simplest version of the Rankine cycle. Before we proceed, let's go back to our understanding of the Carnot cycle. If you will remember, the Carnot cycle under the temperature entropy diagram is rectangular in shape. We can actually trace the Carnot cycle here and compare it to the ideal Rankine cycle. The Carnot cycle starts with stream 1 here, which is a saturated vapor. It is then compressed isentropically to stream 2, which is a saturated mixture, and then compressed isothermally to a certain point here, and then expanded isentropically up to the point that forms a rectangle on the TS diagram. And if we consider the net amount of work generated as the area enclosed by the cycle, the Carnot cycle has a lesser area than the simple Rankine cycle. Okay? Because this five-sided polygon for the ideal Rankine cycle has a bigger area than its equivalent rectangle representing the Carnot cycle. If you further want to increase the amount of work generated for the Rankine cycle, you can take a look at streams 1' and 2' here. Stream 1' represents the case for a superheated vapor entering our turbine. If you start with 1', which is a superheated vapor, and then this passes through a turbine isentropically, in which its output is 2', you can see that the total area enclosed for the Rankine cycle containing superheat is larger than that of the simple Rankine cycle. We will go back to that idea later. But for now, let's try to solve this example. In a Rankine cycle with water as the working fluid, saturated vapor enters the turbine at 8 megapascals and saturated liquid exits the condenser at a pressure of 0.08 megapascals. The net power output of the cycle is 100 megawatts. We want to determine the thermal efficiency, the mass flow rate of steam, the rate of heat transfer in the boiler, and the rate of heat transfer in the condenser. Here we have an illustration of our problem. So we have our 4-step Rankine cycle here. We have the turbine, condenser, pump, and boiler. We also have our 4 streams mapped against the 4 most important properties that we need to complete before we proceed with the problem. This mapping of temperature, pressure, specific enthalpy, and specific entropy for all of the 4 streams is not needed in all of the problems involving Rankine cycles, but it is a very important tool in understanding and interpreting the Rankine cycle. So for instance, in stream 1, we were given a saturated vapor at a pressure of 8 megapascals. So we have here stream 1, 8 megapascals of pressure. Also, it was stated in the problem that in stream 3, we have a saturated liquid at a pressure of 0.08 megapascals. Since we know that stream 1 is a saturated vapor, we can use that knowledge along with the pressure to determine its saturation temperature as well as its specific enthalpy and entropy. From steam tables, at a pressure of 8,000 kilopascals or 8 megapascals, our saturation temperature is 295.06, that is degrees Celsius. From this data, we can now determine the enthalpy and entropy for stream 1. The specific enthalpy of saturated vapor at this pressure and temperature is 2757.94. This is in kilojoules per kilogram. And for specific entropy, we have 5.74. This is in kilojoules per kilogram per Kelvin. We have completed the properties of stream 1. Now let's complete the properties of stream 3. Stream 3 exists as a saturated liquid at a pressure of 0.08 megapascals or 80 kilopascals. Under these conditions, our saturation temperature is 93.34 degrees Celsius. Similarly, for specific enthalpy, we have 390.98 kilojoules per kilogram. And finally, for specific entropy, we have 1.2308 kilojoules per kilogram Kelvin. All of these values are determined from the saturated steam tables. Now it's time to fill in the blanks because we need to know the properties of stream 2 and stream 4. Stream 2 is the outlets of the turbine, and stream 4 is the outlets of the pump. Going back to the basics of the ideal Rankine cycle, we know that the turbine and the pump are operating isentropically. Therefore, stream 1 and stream 2 will have the same specific entropy, while stream 3 and stream 4 also have the same specific entropy. We therefore say stream 2 has a specific entropy of 5.7431 kilojoules per kilogram per Kelvin, and stream 4 has an entropy of 1.2308 kilojoules per kilogram per Kelvin. We still cannot characterize stream 2 and stream 4 because they only have one value for the properties. We need a minimum of 2. So where can we get an additional value so that we can solve the problem? Remember that one of the common assumptions in the ideal Rankine cycle is that the processes in the boiler and in the condenser are happening isobarically, meaning it's a constant pressure process. For that, we say that stream 2, the inlet to the condenser, and stream 3, the outlet to the condenser, share the same pressure. Stream 2 is also at 0.08 megapascals, while stream 4 would need to share the same pressure as stream 1. Therefore, stream 4 has a pressure of 8 megapascals. At this point, for stream 2 and stream 4, we each have two values of the parameters. So we can now determine their temperature and their specific enthalpy. The specific enthalpy is much more important in this case because we are using specific enthalpy values to determine the majority of our unknown parameters, such as efficiency and the rates of heat absorption and heat rejection. Let us first complete stream 2. Stream 2 is a saturated mixture of vapor and liquid. And for that, we first have to determine its quality coming from the specific entropy value. The saturation temperature for stream 2 in this case is still 93.34 degrees Celsius because this is a saturated mixture. And then let's solve for the quality. Here we have the interpolated values for the specific entropy of saturated liquid and saturated vapor. Our formula, this is the quality of stream 2, and that is the specific entropy of stream 2 minus the specific entropy of stream 2 liquid over stream 2 vapor minus stream 2 liquid. Substituting, that is 5.7431 minus 1.2308 divided by 7.4369 minus 1.2308. Our steam quality is 72.71% or 0.7271. With this value of the quality, we can now estimate the value of H2. Here, I have listed the interpolated values of the specific enthalpy of the liquid and the vapor at stream 2 conditions. From this, we can determine the value of H2 by the formula H2L plus X times H2V minus H2L. Substituting, 93.34 plus our determined value of quality is 0.7271 times the difference 2274.48 minus 93.34. H2 is 1679.25 kilojoules per kilogram. Let's go back. Finally, we have stream 4. Stream 4 from our TS diagram is a compressed or subcooled liquid. Again, we simply visit the compressed water tables, and from that, we can determine the value of the specific enthalpy. After the interpolation, we have a value of the specific enthalpy of 399.58 kilojoules per kilogram and a temperature of 93.9 degrees Celsius. We have now completed our table, and it's now time to solve for the required. The first unknown is the thermal efficiency of the cycle. As we have discussed earlier, the thermal efficiency of a Rankine cycle is equal to what you get over what you paid for. What we get is the net work generated in the process, and that is the absolute value of the work generated by the turbine minus the work consumed by the pump divided by what we paid for, and that is the heat absorbed in the boiler. Expressing this in terms of enthalpies, since mass flow rate is constant, for the turbine, that is enthalpy 2 minus enthalpy 1. For the pump, that is enthalpy 4 minus enthalpy 3. And finally, for the boiler, that is enthalpy 1 minus enthalpy 4. Since we already have all of these enthalpy values, thanks to our filling of the table earlier, we can directly substitute the values and then solve for the efficiency of the cycle. The efficiency is 0.4537. Next, let us determine the mass flow rate of steam in the system. The mass flow rate of the steam can be determined from the given net power generation. The net power generated, as stated in the problem, was 100 megawatts. This is equal to 100,000 kilowatts. We also characterize the net work or the net power generated as mass flow rate multiplied by the net specific work. The net specific work is simply a function of the work generated by the turbine and the work consumed by the pump. So that is absolute value of the work generated by the turbine minus the work consumed by the pump. These are all in specific work. Therefore, we characterize the net specific work as H1 minus H2 minus quantity H4 minus H3. You can substitute the enthalpy values that we have obtained earlier. For that, we solve the net specific work as 1070.09 kilojoules per kilogram. From here, we can determine the mass flow rate of the steam as the net power generation over the net specific work. That is 100,000 kilowatts divided by 1070.09 kilojoules per kilogram. The answer is 93.45 kilograms per second. This is the mass flow rate of our working fluid steam. Next, let us solve for the rate of heat transfer in the boiler. The rate of heat absorbed in the boiler is simply the mass flow rate of steam, our working fluid, multiplied by the enthalpy change, that is H1 minus H4. Substituting all of the given values, the heat transfer from the boiler is equal to 220,389 kilowatts, or just equal to 220 megawatts. Finally, for letter D, we also need to determine the heat rejection rates in the condenser, or the heat that is rejected in the process. Q condenser is equal to mass flow rate multiplied by H3 minus H2. Substituting, we get a value of negative 120,389 kilowatts, or that is negative 120 megawatts. There is a negative sign because again, heat is being rejected. To check our answers, let us perform an energy balance. The energy balance for the system is simply all of the energy coming in is equal to all of the energy coming out. This time, it will be helpful if we simply get all of the absolute values of the energies involved. We can write our energy balance as the rate of heat addition in the boiler is equal to the rate of power generation, that is net, plus the rate of heat rejection in the condenser. If we use the absolute values of all of these parameters, we have 220 megawatts from the boiler, 100 megawatts net power generation, and 120 megawatts heat rejection in the condenser. We see that both sides of the equation are equal, therefore we have confidence in our solution being correct. Okay, that is how we solve problems involving the ideal Rankine cycle. Let's go back to the diagram. For you to be able to solve these kinds of problems, it is important that you understand how the Rankine cycle works. So from now on, I would suggest that you first draw the entire Rankine cycle, just as what we did here. You label where is the heat coming in, where is the heat coming out, and is there consumption and generation of work, and you construct the same table that we constructed here. It simply shows all of the streams along with the four most important parameters: temperature, pressure, enthalpy, and entropy. After you have completed this table, it will be easier for you to determine thermal efficiency values, mass flow rate of steam, and other parameters. This is how we approach such problems. Let's go back. In contrast to the ideal Rankine cycle, let us now discuss the real Rankine cycle. The real or non-ideal Rankine cycle accounts for irreversibilities in the components of the cycle, mainly in the turbine and in the pump. Review the definitions of isentropic efficiencies of turbines and pumps because we will be using those in these types of problems. If you take a look at our new temperature entropy diagram, from stream 1 to stream 2, in the ideal Rankine cycle, that is just a straight vertical line because we were assuming that the turbine is operating isentropically, constant entropy. For a real Rankine cycle with an imperfect turbine, take note that the actual entropy of stream 2 is greater than that of stream 1. That's because the imperfections in the turbine is generating entropy. So it's no longer a straight line. Okay? The same is true for the pump. From stream 3 to stream 4, you can see that in the ideal Rankine cycle, that was previously a straight vertical line, indicating that the pump is operating isentropically. For the real Rankine cycle, stream 4 has a higher entropy than stream 3 because again of entropy generation. That's why this is now a slanted line. Other than that, it's still the same as the previous case. We have step 1, that's fluid expansion, but we have an imperfect turbine. Step 2, we have isobaric compression in the condenser. Step 3, we have fluid compression in an imperfect pump. And then step 4 is the isobaric expansion in the boiler. Let's try to solve an example, and we will see what will change in our solution. We will be solving the same problem. So that is the Rankine cycle with water as the working fluid. The saturated vapor enters the turbine at 8 megapascals and saturated liquid exits the condenser at 0.08 megapascal. However, in this example, both the turbine and the pump has efficiencies of 85%. The net power output of the cycle is still 100 megawatts, and we want to determine the following. Here we have the given for the problem. We have the same properties for stream 1 and stream 3 because nothing changed there. Stream 1 is still a saturated vapor at 8 megapascals and stream 3 is still saturated liquid at 0.08 megapascals. What will change here is the approach on how we determine the value of the entropy of stream 2 and stream 4. If we go back to our previous example, the specific entropy of stream 2 is equal to the specific entropy of stream 1 because the turbine was operating isentropically. In this case, we have to use the given value for the isentropic efficiency to estimate entropy 2 and entropy 4. From our previous discussions, the isentropic efficiency of a turbine is equal to the actual work over the isentropic work. In terms of the enthalpies, this is H2 minus H1 actual divided by H2S minus H1. H2S is the specific enthalpy of stream 2 under isentropic conditions. The value of H2S can be retrieved from our previous example because that was an isentropic operation. So this is 1679.25 kilojoules per kilogram. We have our value of H1, that is 2757.94 kilojoules per kilogram. So what we can determine from this equation is the value of H2 or the actual stream 2 entropy given the isentropic efficiency of the turbine, that is 85% or 0.85. Rearranging this equation and solving for H2, we have 0.85 times H2S 1679.25 minus H1 2757.94 plus H1 2757.94. The actual enthalpy of stream 2 is equal to 1841.05 kilojoules per kilogram. In the same token, we define the isentropic efficiency of a pump as the isentropic work over the actual work. In terms of enthalpies, this is H4 minus H3 divided by H4S minus H3. H4S is the specific enthalpy of stream 4 under isentropic conditions. And we can get this again from our previous example wherein we have isentropic conditions. The value of this is 399.58 kilojoules per kilogram. The isentropic efficiency of the pump is also 85%. So from this knowledge, we can rearrange this equation and solve for H4 or the actual enthalpy of stream 4. That is 0.85 multiplied by H4S 399.58 minus H3 390.98 plus H3 390.98. Our H4 is equal to 398.29 kilojoules per kilogram. Let's go back to our summary table. We now have completed all of the enthalpy values in our table, and we can actually proceed in solving the rest of the unknown quantities. Of course, our solution here is a little bit shorter because we already had an idea of the isentropic enthalpies in stream 2 and stream 4. However, if you are presented with a different problem involving the non-ideal Rankine cycle, you do have to complete the values in this table for you to have the complete view of the problem. Okay? For now, let's solve for the thermal efficiency. We have here the formula for determining the thermal efficiency of the non-ideal Rankine cycle. It's still the same formula, but the values of H2 and H4 are now different for this problem. Substituting, that is H1 2757.94 minus H2 1841.05 minus H4 minus H3, so that is 398.29 minus 390.98 divided by H1 2757.94 minus H4 398.29. Our new efficiency is only 0.3855. Our 38.55% efficiency in the non-ideal Rankine cycle is lower compared to the 45% efficiency that we have solved earlier for the ideal Rankine cycle. By simply considering that our pump and our turbine are only 85% efficient, you see that we have a large decrease in the efficiency of the cycle. In reality, there are more factors that contribute to the decrease of the efficiency of the Rankine cycle if we are now considering real conditions. Let's solve for the mass flow rate and then compare it with the previous value that we had. The mass flow rate is equal to the net power generation divided by the net specific work. The net specific work is actually the numerator of our thermal efficiency formula. Solving for mass flow rates, we have a net power generation of 100,000 kilowatts divided by H1 2757.94 minus H2 1841.05 minus H4 398.29 minus H3 390.98. The required mass flow rate of steam this time is 109.94 kilograms per second. This is larger compared to the mass flow rate obtained in the ideal Rankine cycle for the same conditions. This happens because as there are more inefficiencies and more irreversibilities in our system, we need to provide the cycle with more steam or more of the working fluid just to achieve the same net power generation as that of the ideal Rankine cycle. In a real power plant, the increase in the required mass flow rate of steam would translate to an increase in operating costs. So you see that as we increase the irreversibility of the turbine and the pump, we are increasing the mass flow rate, which also affects the operating cost of a power plant. In addition to that, our thermal efficiency is lower than that of the ideal Rankine cycle. These are some things that we simply need to accept because there is no remedy for the second law of thermodynamics. All of these irreversibilities and decreases in efficiencies are all caused by the second law of thermodynamics. Let us solve for the heat flows to and from the boiler and the condenser. For the boiler, that is the mass flow rates multiplied by H1 minus H4. Substituting, we have the mass flow rate here, 109.94 kilograms per second, multiplied by H1, 2757.94 minus H4, 398.29. Our answer is 259 megawatts. Next, our Q condenser is equal to mass flow rate times H3 minus H2. That is 109.94 mass flow rate times H3, 390.98 minus H2, 1841.05. Our Q condenser is equal to negative 159 megawatts. Our energy balance, Q boiler, is equal to net work generation, absolute value, plus the absolute value of Q condenser. That is 259 is equal to 100 plus 159 megawatts. This is again equal, meaning that our solution is correct. That is how we approach the solution for non-ideal Rankine cycle. Let's go back. The next thing that we will consider are modifications to improve the performance of the Rankine cycle. The simple 4-step Rankine cycle is limited in its output work and efficiency to convert work from heat. We have here several modifications to the process to increase its efficiency and output. First, we have reheats and superheat, and second, we have regeneration, both open and closed feed water heaters. Let's start with reheat and superheat. This is the diagram for Rankine cycle with reheats. When we say reheat, we are simply increasing the temperature of the output of the first stage of the turbine before feeding it to the second stage of the turbine. This extra step ensures that your steam will not condense inside of the turbine. The condensing of the steam inside the turbine will decrease its performance. By doing this reheat step, we have added several steps into the cycle. Let's start with stream number 1. Stream number 1 is the output of the boiler and the input of the first stage of the turbine. The output of the first stage of the turbine is stream number 2, and this goes back to the boiler to reheat the output of the turbine. After reheating, we have stream 3. Stream 3 is the input to the second stage of the turbine. The output to the second stage of the turbine is stream 4. This then passes through the condenser wherein heat is being rejected, and then we go to the pump, and then we go back to the boiler. Everything else is the same. We simply added reheat steps, and we have divided the turbine into two distinct parts, the high pressure part and the low pressure part. If we look at the temperature entropy diagram, if you start with stream 1 is already a superheated steam. After passing through the turbine, this is an isentropic turbine, its temperature drops to T2 in stream 2, and then by inserting stream 2 in the boiler, we are able to increase its temperature from T2 to T3. From stream 3, this then enters the condenser and then the pump and then the boiler. And the cycle repeats itself. So the modification for reheats is only in this part. Also, by having stream 1 as a superheated steam, we are practicing what we call superheat. The superheater is part of the boiler wherein we are raising the temperature of the steam beyond its saturation temperature. The superheating of the steam provides more value to the extraction of the work in the turbine. Let's try to solve an example. Steam enters the first stage of the turbine at 8 megapascals, 480 degrees Celsius, and expands to 0.7 megapascals. It is reheated to 440 degrees Celsius before entering the second stage of the turbine, where it expands to the condenser pressure of 0.08 megapascals. The net power output is 100 megawatts. This is basically the same problem as before, but now we are dividing the turbine into two stages. The first stage is here, and the second stage is here. And we will be determining the same 4 parameters that we have determined for the previous problems. Here are the given for the problem. So we have updated our diagram. This is now the Rankine cycle with reheats and superheat. We have a total of 6 streams. And as with the previous problem, we first need to complete this table, especially the values of the enthalpies, before we can solve for the other parameters. We are only given the temperature and pressure of stream 1. So at 8 megapascals and 480 degrees Celsius, this is a superheated steam. From the steam tables, we have a specific enthalpy of 3349.02 kilojoules per kilogram and a specific entropy of 6.6591 kilojoules per kilogram per Kelvin. Upon assumption that both stages of the turbine are operating isentropically because we were not given isentropic efficiencies, stream 1 and stream 2 have the same entropy, 6.6591. Similarly, the inputs and outputs of the second stage of the turbine, that is stream 3 and stream 4, also have the same entropies, but we will determine that later. For now, let us check the states of stream 2. For a pressure of 0.7 megapascals and an entropy of 6.6591 kilojoules per kilogram per Kelvin, stream 2 is a saturated mixture of vapor and liquid. For that, we have to determine its quality, and then we can solve for the enthalpy of stream 2. I have determined the quality of the steam to be 0.99, and then with that, we can solve for the enthalpy of stream 2. I have determined the value of the specific enthalpy as 2739.75 kilojoules per kilogram. Now, let us take a look at stream 3 and ponder how do we determine the value of one of its parameters because we are only given one, that is 440 degrees Celsius. If you take a look at stream 2 and stream 3, they both pass through the boiler. And the processes that pass through the boiler and the condenser are considered isobaric, meaning they have constant pressure. Therefore, we can say that the pressure of stream 2 is equal to the pressure of stream 3, and that is 0.7 megapascals for stream 3 as well. Now we have two parameters for stream 3, 440 degrees Celsius and 0.7 megapascals. According to the steam tables, this is still a superheated steam. Also from the steam tables, we have determined the enthalpy to be 3354 kilojoules per kilogram, and the specific entropy is 7.763 kilojoules per kilogram per Kelvin. We have completed the parameters on stream 3. Stream 3 is the inlet for the second stage of the turbine, and stream 4 is the outlet of that second stage. And assuming that the turbine operates isentropically, the specific entropy of stream 4 is also 7.763 kilojoules per kilogram per Kelvin. We now have two parameters for stream 4, so we can determine the state of the working fluid. Based on the steam tables, at these conditions for stream 4, it is still a superheated steam. I am leaving this for you to verify, but the value of the specific enthalpy is 2789.52 kilojoules per kilogram per Kelvin. Next, let us decipher stream 5. It was not stated in the problem, but we can assume that stream 5 is a saturated liquid. The output of condensers are typically saturated liquids to maximize the performance of the plant. So if stream 5 is a saturated liquid, we only need to know one value of its parameters. And for that, we know that we can get its pressure because the condenser again is isobaric. So stream 4 and stream 5 have the same pressure. That is 0.08 megapascals. With the knowledge of the pressure and that is it is a saturated liquid, we can determine its enthalpy. From the steam tables, that is 391.71 kilojoules per kilogram. Also from the steam tables, we can get the value of the specific entropy of stream 5, that is 1.233 kilojoules per kilogram per Kelvin. Why is this value important? That's because streams 5 and 6 are the inputs and outputs of the pump. And if we are assuming that the pump is operating isentropically, we can say that the entropy of stream 6 is also 1.233 kilojoules per kilogram per Kelvin. Now we need another value of the parameters of stream 6 in order to describe it fully. So we now have its entropy, but we can also get its pressure. If you take a look at stream 6 and stream 1, stream 6 is the inlet to the boiler, stream 1 is the outlet to the boiler. Therefore, we can say that stream 6 and stream 1 have the same pressures. Remember that the boiler and the condenser are operating isobarically. Stream 6 also at a pressure of 8 megapascals. For stream 6, a pressure of 8 megapascals and an entropy of 1.233 kilojoules per kilogram per Kelvin means that it is a subcooled or compressed liquid. From the steam tables, you can again estimate the value of the specific enthalpy. That is 400.38 kilojoules per kilogram. And with that, we have completed all of the values of the enthalpies for the 6 streams. We can now move on to the unknowns of the problem. The efficiency of the cycle would still be the same in definition, that is, what we get over what we paid for. What we get is the network, but this time, the network consists of the total power generated by the two stages of the turbine minus the power consumed by the pump. So we write that as the absolute value of the work generated on the first stage of the turbine plus the work generated on the second stage of the turbine minus the work consumed by the pump over what we paid for, that is still Q boiler. Okay? We can also have this expression in terms of the specific works instead of the work rates. Let us define the specific energies for this equation. We have the specific work output of the first stage of the turbine, that is equal to H2 minus H1. We have the specific work output of the second stage of the turbine, that is H4 minus H3. And the specific work of the pump, that is H6 minus H5. Let's compute all of this first. the work of the first stage of the turbine, that is H2 minus H1, or we can have it as H1 minus H2 for it to have the absolute value, that is 3349.02 minus 2739.75, 609.27 kilojoules per kilogram. Next, for the work generated by the second stage of the turbine, we can also have that as H3 minus H4 to make it the absolute value, 3354 minus 2789.52, 564.48 kilojoules per kilogram. Next, for the pump, that is H6 minus H5, 400.38 minus 391.71, 8.67 kilojoules per kilogram. If you compare the magnitudes of the power generation and the power consumption, the power generation is much more greater than the power consumption. Okay? Nevertheless, it is still important to include the contributions of the pump in the process. Next, let us consider the Q boiler, or the heat absorbed in the boiler. In our previous examples, the calculation in the heat absorbed in the boiler only consists of two enthalpies because that's the inlet and the outlet of the boiler. In this case, if we go back, you would see that there are two inputs and two outputs to the boiler. Your inputs are stream 6 and stream 2, and your outputs are stream 1 and stream 3. Therefore, we need to see four enthalpy terms in our determination of Q boiler. That will be H1 minus H6 plus H3 minus H2. You need to take note of this variation. Solving the value, we have H1 is 3349.02 minus H6 400.38 plus H3 3354 minus H2 2739.75. Our total Q boiler is equal to 3562.89 kilojoules per kilogram. We can now substitute all of these values to our definition of the efficiency. That is 609.27, the work output of the first stage of the turbine, plus 564.48, the work output of the second stage, minus 8.67, divided by 3562.89. The efficiency of the cycle is 0.327. At first glance to this value of the efficiency, it seems that this has a lower efficiency compared to the ideal simple Rankine cycle. But we should also take a look at the values of the mass flow rate of the working fluid, as well as the heat rate of absorption and rejection in the boiler and the condenser, to truly see what is happening here. As with the other examples, we determine the mass flow rates of the working fluid as the net power generation over the net specific work. We have determined the net specific work from the previous part of this problem, and the net power generation is still 100,000 kilowatts or 100 megawatts. Substituting those values, we have 100,000 divided by 609.27 plus 564.48 minus 8.67. The mass flow rate of steam is 85.83 kilograms per second. This is a lower mass flow rate compared to the simple Rankine cycle. This means that this cycle needs less of the working fluid circulating through the processes. Also, this mass flow rate has an effect on the heat absorption in the boiler and the rate of heat rejection in the condenser. Let us solve for the rate of heat addition in the boiler. This is equal to the mass flow rate multiplied by the specific heat absorbed in the boiler. Earlier, we have determined this value to be equal to 3562.89, and we multiply this with 85.83 kilograms per second. Our rate of heat addition is equal to 306 megawatts. And finally, we solve for the rate of heat rejection in the condenser. This is equal to the mass flow rate times H5 minus H4. We have a mass flow rate of 85.83 kilograms per second multiplied to 391.71 minus 2789.52. Our rate of heat rejection in absolute value is 206 megawatts. If you perform the energy balance, the energy input is equal to the energy output. We really cannot directly compare this Rankine cycle with reheat and superheat with that of the basic Rankine cycle. That's because the two cycles have different states of steam that is exiting the boiler. Also, the exiting pressure of the turbine must be optimized such that the state of the steam that is entering the condenser is either a saturated vapor or a saturated mixture. In our case, the stream that is exiting the second stage of the turbine is still a superheated steam, which still carries a significant amount of energy that is simply wasted by directly discharging it into the condenser. Okay? But generally, the inclusion of reheat and superheat are beneficial for the efficiency of a steam power plant as long as the discharge conditions of the final stage of the turbine are optimized. Let's go back. Another modification to the Rankine cycle is the addition of regeneration. In regenerative Rankine cycle, a fraction of the flow after the first stage of the turbine is extracted and redirected to a heater. The heater could either be open or closed. If you take a look at this diagram, for Rankine cycle with reheat, the output of the first stage of the turbine is sent back into the boiler to be reheated, and then the reheated stream will be the input to the second stage of the turbine. In Rankine cycle with regeneration, a part of the flow or a fraction of the flow in the turbine is extracted in the middle, and that stream is fed to an open feed water heater. The purpose of this extracted stream is to heat the water coming out of the condenser such that the liquid water exiting the feed water heater and entering the boiler would be at a higher temperature. If it enters at a higher temperature, it will also exit the boiler at a higher temperature compared if we don't have an open feed water heater. The result of that is the existence of a non-linear pathway for our working fluid. If we start with stream 1 is the outlet of the boiler. The steam enters the first stage of the turbine, and then it goes to the second stage of the turbine. However, a part of that is extracted, as mentioned earlier. The fraction that was extracted enters the open feed water heater. The output of the turbine, that's stream 3, enters the condenser wherein it is condensed from a vapor to a liquid. The liquid condensed from the condenser is then pumped into the open feed water heater. So the liquid stream, that is stream 5, is combined with the vapor stream, that is stream 2, to produce stream 6. Stream 6 is a liquid stream that is at a higher temperature. Stream 6 is then pumped, becomes stream 7, and is then fed to the boiler. If we map this process into a temperature entropy diagram, you would see that typically stream 1 is a superheated vapor. Upon passing the turbine, it is converted to a saturated mixture, that is stream 3. However, stream 2, which is still a superheated vapor, is subtracted from stream 1 and is sent straight to stream number 6. From stream 2 to stream 6, you would see that it is being condensed because from a higher temperature, because it is superheated, it is brought down to its saturation temperature, and then from a saturated vapor here, it is converted to a saturated liquid. So stream 6 is a saturated liquid, meaning it is at its boiling point. If we go back to stream 3 is already a saturated mixture. It's a mixture of vapor and liquid. It is then condensed to stream 4 at the same temperature. From stream 4 to stream 5, we are compressing the liquid water, and we are doing that isentropically because this is a vertical line. And then this is where stream 5 mixes with stream 2 to generate stream number 6. As mentioned earlier, stream 6 is a saturated liquid, and then upon passing through another pump, we increase its temperature and pressure isentropically, and it is then fed to the boiler where it is vaporized to produce stream number 1. That is the entire process of the Rankine cycle with regeneration. For regenerative Rankine cycle, we have two types of heaters. The one presented here is an open feed water heater, meaning that stream number 2 and stream number 5 are mixing. They have direct contact with each other. For that, you can perform a mass balance wherein the mass flow rate of stream 2 plus the mass flow rate of stream 5 is equal to the mass flow rate of stream 6. Likewise, we can perform the same mass balance in the turbine such that the mass flow rate of stream 1 is equal to the mass flow rate of stream 2 plus the mass flow rate of stream 3. That's why you can see here variables like y and 1 minus y. The variable y represents the fraction of the flow that is diverted from the turbine. And the variable 1 minus y is the fraction of the fluid that is sent to the condenser. As mentioned, that is the case for an open feed water heater wherein two streams are mixed together. Another variant of that is what we call the closed feed water heater. In that system, a heat exchanger is used to transfer energy of the steam from the output of the turbine's first stage, that is stream number 2, to the feed of the boiler, that is stream number 6. There is no mixing between the two streams. So if we have a closed feed water heater, this is often a shell and tube heat exchanger wherein the two streams are not allowed to mix with each other. So they are just transferring their energy but not their mass. There are some key differences between the Rankine cycle with closed and open feed water heaters. For the closed feed water heater, notice that stream number 2 enters the heater and then exits as stream number 7. Stream number 7 is then recycled back into the condenser. Stream number 3, which is the remainder of the steam after we have obtained stream number 2, enters the condenser and joins stream number 8. So for the condenser, we can perform a mass balance, that is, mass flow rate of stream 3 plus the mass flow rate of stream 8 is equal to the mass flow rate of stream number 4. Besides that difference, their concepts are just the same. Let's try to solve an example. We have a regenerative Rankine cycle with an open feed water heater. Steam enters the turbine at 8 megapascals, 480 degrees Celsius, and expands to 0.7 megapascals, where some of the steam is extracted and diverted to the open feed water heater operating at 0.7 megapascals. The remaining steam expands through the second stage of the turbine to 0.08 megapascals. Saturated liquid exits the open feed water heater at 0.7 megapascals. Both turbine stages operate at 85% efficiency, while both pumps are operating isentropically. The net output is 100 megawatts, and we are to determine the same parameters that we have been solving for the other problems. Here are the given to the problem. We have here our diagram for the regenerative Rankine cycle with an open feed water heater, and we have our usual table of streams and their properties. For stream number 1, this is the same as our previous problem, so it is at 480 degrees Celsius, 8 megapascals, and by looking at the superheated steam tables, we have the values of specific enthalpy and specific entropy. For stream number 2 and 3, we can determine their specific enthalpies by considering the thermal efficiency of the turbine given as 85%. For that, we say that the thermal efficiency of the first stage of the turbine is equal to actual work over isentropic work. This is also equal to H2 minus H1 over H2S minus H1. From the previous problem, we have determined the value of H2S, or the isentropic enthalpy of the second stream, is equal to 2739.75 kilojoules per kilogram. Remember that this is at 0.07 megapascals of pressure and a specific entropy equal to that of stream 1. Since we know that the efficiency of both stages of the turbine is 85%, we can now rearrange this equation to solve for the value of H2, or the actual enthalpy. That is 0.85 times 2739.75 minus H1. H1 is 3349.02 kilojoules per kilogram. And then we add the value of H1, 3349.02. Our H2 is 2831.14 kilojoules per kilogram. The same analysis can be applied to the second stage of the turbine. We say that the efficiency of the second stage of the turbine is the actual work over the isentropic work, that is equal to H3 minus H2 over H3S minus H2. Before we proceed with the calculation, we have to evaluate the value of H3S. This has to be evaluated under isentropic conditions. Therefore, it should be at P3 is equal to 0.08 megapascals and a value of S3, which is equal to S2, which is also equal to S1, that is 6.6591 kilojoules per kilogram per Kelvin. Under these conditions, stream 3 is a saturated mixture. It has a quality of 87.5%, and I have determined its value to be equal to 2381.13 kilojoules per kilogram. Rearranging our equation for efficiency, we can now solve for the value of H3, or the actual enthalpy. that is 0.85 times 2381.13. This is your H3S minus H2, 2831.14. And then we add the value of H2, 2831.14. Our H3 is 2448.63 kilojoules per kilogram. Let's go back to our table. We are done with the analysis of streams 1, 2, and 3 because we already have their enthalpies. For stream number 4, which is the outlet of the condenser, again, we will be assuming that that is a saturated liquid. Stream number 4 being the output of the condenser and stream number 3 being its input. If the condenser operates isobarically, therefore stream number 4 also has a pressure of 0.08 megapascals. The knowledge of this pressure and that the stream contains saturated liquid can help us find the value of the enthalpy. From the steam tables, this is 391.71 kilojoules per kilogram. Also, we need to determine the specific entropy at stream number 4 because that is the inlet to our first pump. From the steam tables, that is 1.233 kilojoules per kilogram per Kelvin. Since it was stated that both pumps are operating isentropically, stream 5 also has a specific entropy of 1.233 kilojoules per kilogram per Kelvin. Another assumption that we can make is that the open feed water heater also operates isobarically. From that assumption, we can say that the pressure of stream 6 is equal to the pressure of stream 2 is also equal to the pressure of stream 5. Therefore, stream 5 also has a pressure of 0.7 megapascals. With the knowledge of the pressure and entropy in stream number 5, we can consult the steam tables to determine its enthalpy. For the subcooled or compressed water steam table, after double interpolation, the value of the enthalpy is 392.85 kilojoules per kilogram. Next, for stream 6, we can use the information that it is a saturated liquid and its pressure is 0.7 megapascals to determine its enthalpy. From the steam tables, the value is 695.62 kilojoules per kilogram. Also for stream 6, we have to determine its specific entropy because it is the inlet to the pump and we need the value of the entropy to determine the properties of stream number 7. So for stream number 6, the specific entropy of the saturated liquid is 1.9883 kilojoules per kilogram per Kelvin. Because the second pump is isentropic, this value also applies to stream number 7, which is the output of the second pump. Also for stream number 7, we know its pressure because upon the assumption that the boiler operates isobarically, the pressure of stream 1, which is 8 megapascals, is equal to the pressure of stream number 7. Now that we know the pressure and the entropy in stream number 7, we can determine its specific enthalpy. Under these conditions, our working fluid is a compressed or a subcooled fluid with a specific enthalpy of 703.95 kilojoules per kilogram per Kelvin. And with that, we have completed our enthalpy values. We can now move on and solve for the required parameters. Before we solve for the cycle efficiency, let's first solve for the energy flow terms, that is, the work generated by the turbines, the work consumed by the pumps, and the heat flows in the boiler and in the condenser. Let's start with the specific work of the first stage of the turbine. This is equal to H2 minus H1. For the second stage of the turbine, this is equal to H3 minus H2. For the first pump, this is H5 minus H4. And for the second pump, this is H7 minus H6. For the boiler, that is H1 minus H7. And for the condenser, that is H4 minus H3. Solving for their absolute values, the work generated by the first stage of the turbine is equal to 517.88 kilojoules per kilogram. For the second stage, that is 382.51 kilojoules per kilogram. For the work consumed of the first pump, that is 1.14 kilojoules per kilogram. And the work consumed by the second pump is equal to 8.33 kilojoules per kilogram. The amount of heat absorbed in the boiler is 2,645.25 kilojoules per kilogram. And finally, the heat rejected in the condenser is equal to 2056.92 kilojoules per kilogram. Again, these are all absolute values. If we write our expression for the efficiency of the cycle, in the numerator we will have the absolute value of the rates of work generation by the first part of the turbine plus the rate of work generation of the second part of the turbine minus the work consumed by the pumps, that's pump 1 and pump 2, divided by Q boiler. Now, in the past examples, we have been canceling the mass flow rate of all of this because we only have a single flow of the working fluid. Thus, the mass flow rate is constant. However, in the case of regenerative Rankine cycle, the mass flow rates are different for certain streams. For example, mass flow rate of stream 1 is different from the mass flow rates of stream 2 and 3. Also, the mass flow rates surrounding the open feed water heater are also different. Thus, our efficiency would have to be solved as mass flow rate of stream 1 times H1 minus H2 plus mass flow rate of stream 2 times H2 minus H3 minus the mass flow rate of stream 4 times H5 minus H4 minus the mass flow rate of stream 6 times H7 minus H6. And for our denominator, that is mass flow rate of stream 1 times H1 minus H7. To further simplify this problem, we have to solve for the value of y. Remember that this parameter is equal to the ratio of the mass flow rate of stream number 2, that is the stream going into the open feed water heater, divided by stream number 1, that is the mother stream or the original stream. In the same token, the parameter 1 minus y is equal to the mass flow rate of stream 3 over the mass flow rate of stream 1. Our mass balance is mass flow rate of 1 is equal to mass flow rate of 2 plus the mass flow rate of 3. We also need to perform the energy balance around the open feed water heater. That is mass flow rate 2 enthalpy 2 plus mass flow rate 5 enthalpy 5 is equal to mass flow rate 6 enthalpy 6. We will be applying some equivalencies here. For example, mass flow rate 6 is equal to mass flow rate 1 and mass flow rate 5 is equal to mass flow rate 3. This relates our energy balance on the open feed water heater to our overall mass balance equation. Substituting, this becomes mass flow rate 2 enthalpy 2 plus mass flow rate 3 enthalpy 5 is equal to mass flow rate 1 enthalpy 6. If we divide both sides by the mass flow rate of stream 1, we will get H6 is equal to M2 over M1 is equal to Y. So that is Y H2 plus M3 over M1 is equal to 1 minus Y. This becomes 1 minus Y H5. This resulting equation is now a function of Y and enthalpies. This tells us that we can already determine the value of Y or the fraction of flow diverted into the open feed water heater just by determining the values of the enthalpies of stream 2, 5, and 6. Let us isolate the variable y on one side of the equation. Expanding, this is H6 is equal to YH2 plus H5 minus YH5. Factoring out, H6 is equal to Y times H2 minus H5 plus H5. Rearranging, we now have the final form of the equation. Y is equal to H6 minus H5 over H2 minus H5. This equation applies to all regenerative Rankine cycles with an open feed water heater. This will not apply to the closed feed water heater. Okay? This determination of the value of Y will help us to determine the value of the efficiency of the cycle. Substituting our enthalpies, this is H6 695.62 minus H5 392.85 divided by H2 2831 0.14 minus H5, 392.85. Our Y is 0.1242. We will use this value in the determination of our overall efficiency. Let me first erase the derivation and then we'll proceed. Going back to our equation for efficiency, we write it as mass flow rate 1, WT1, plus mass flow rate 3, WT2. Remember that mass flow rate 3 is the flow of the working fluid into the second stage of the turbine, minus mass flow rate 3, WP1, minus mass flow rate 1, WP2. You can take a look at our diagram and verify that mass flow rate 1 goes through pump 2 and mass flow rate 3 goes through pump 1. And that is divided by mass flow rate 1 Q boiler. Now it's time to substitute the definition of Y into our equation for efficiency. This equation can now be rewritten as mass flow rate 1 WT1 plus mass flow rate 1 minus Y WT2 minus mass flow rate 1 minus Y WP1 minus mass flow rate 1 WP2 all over mass flow rate 1 QB. You can now see the utility of expressing our equation in terms of Y. We can now cancel M sub 1. M1 cancels. We are now left with parameters that we already have values for. Let's directly substitute. In our numerator, that is WT1 517.88 plus 1 minus Y, 1 minus 0.1242 times WT2 382.51 minus 1 minus Y, 1 minus 0.1242 times WP1 1.14 minus WP2 8.33. In the denominator, we have Q sub B 2645.25. Our efficiency is 31.89% or 0.3189. Let us now determine the mass flow rate of the working fluid in the system. Now you have to be careful for the regenerative Rankine cycle because this mass flow rate is only equal to mass flow rates of stream number 1. Our offshoots, such as the mass flow rate of stream 2 and 3, will give you the wrong answer. So please keep this in mind. However, even with that, we still solve for the mass flow rate as the net power generation over the net work. The net work is now defined as WT1 plus 1 minus Y WT2 minus 1 minus Y WP1 minus WP2. This is basically the numerator in our equation for efficiency. We solve this as 100,000 kilowatts. This is our net power generation divided by WT1 is 517.88 plus 1 minus 0.1242 times 382.51 minus 1 minus 0.1242 times the work consumed by pump 1, 1.14 minus work consumed by pump 2, 8.33. Our mass flow rate is equal to 118.55 kilograms per second. With that, we can also solve for the Q boiler or the net rate of heat absorption in the boiler. This is mass flow rate 1 multiplied by Q boiler. Our mass flow rate is already given here, 118.55 multiplied by Q sub B, that's 2645.25. Our net rate of heat absorption is equal to 314 megawatts. Finally, letter D, we have the net rate of release of energy in the condenser. That's equal to mass flow rate of stream 3 times QC. Take note that only stream 3 goes through the condenser. So that is the only one that we will consider. The mass flow rate of stream 3 is equal to mass flow rate of stream 1 times 1 minus y. So we can use this equation. Mass flow rate of stream 1 is 118.55 times 1 minus y, 1 minus 0.1242 times QC. QC is 2056.92. Our rate of heat rejection in the condenser is 214 megawatts. If you check our energy balance, it's still valid. That is Q boiler is equal to W net plus Q condenser. That is 314 is equal to 214 plus 100 megawatts. So it's still balanced. With this example, we saw that there are differences between the approach in the solution of the regenerative Rankine cycle compared to the Rankine cycle with reheat and superheat or the simple Rankine cycle. Please do take note of those differences. Let's go back and let's close this lesson with some of the key takeaways. First, the analysis of a Rankine cycle problem is only as good as your illustration of the system and the understanding of the temperature entropy diagram. Thus, when solving any problem involving Rankine cycle, you first need to draw your entire system and you need to construct your table of the streams together with their properties. And as what we have demonstrated earlier, you only need to complete the values of the enthalpies for all of the streams, and with that, you can already determine the efficiency of the cycle as well as other important parameters. Second, the goal of the different alterations of the Rankine cycle is to improve its efficiency of heat conversion to work. For our lesson, we were not able to compare the efficiencies of the alterations of the Rankine cycle to that of the simple one because of the differences in process conditions. With that, you just have to keep in mind that those alterations were invented to increase the overall efficiency of heat conversion to work in the Rankine cycle. That's it for this lesson. I hope you have learned something. Thank you for listening, and as always, keep safe.